Alright, so in this video we begin chapter 11, which is a new kind of distribution called the chi-square distribution, and we're going to do variance test. So in this chapter we are going to test a claim about standard deviation or variance, and then we are going to apply the chi-square distribution for the goodness of fit test and the test for independence. Alright, so far what we have done. We have done hypothesis testing for the proportion and for the mean of a population. Alright, however, one of the most important tests right here is that of the standard deviation, in which, well, this one is more applied in the industry, in which we want to improve the consistency of a product. What do we mean by that? Well, by reducing the standard deviation among the sample or the population. All right, so so in this case we are going to do some tests of variation. We're going to do hypothesis testing for standard deviation or variance, no more means or proportion. But in this case, for this kind of test, we're going to need a new kind of distribution, which is called the chi-square distribution. Well, in this case, as opposed to the normal distribution and the t-distribution, in this case, the chi-square distribution, it's a distribution that is skewed, is right skewed. Okay, so actually there's many different chi-square distribution, and that has to do with the degrees of freedom. Keep in mind that degrees of freedom come from the sample size that we take. All right, so, and in this case, well, again, we use degrees of freedom just the same way we did for the t-distribution. All right, so this is what happens with the chi-square distribution as the degrees of freedom increase. As the degrees of freedom increase, it becomes, actually, it looks more like a normal distribution or the t-distribution. But that doesn't mean that we can use the normal distribution for this purpose. We still use the chi-square distribution. It's just the shape that it takes as the sample size, and then consequently the degrees of freedom increase. Well, what's next about this? Well, properties of the chi-square curves. Well, on the one hand, property, well, the total area under a chi-square curve equals 1. And well, that's also true for the normal distribution. You know, when we did a normal distribution, we go from 0 to 1. Well, the area adds up to 1. Same for the t-distribution, which looks a lot like the normal distribution, from 0 to 1. And the total area underneath is equal to 1. All right, now what's different about the chi-square distribution? So in this case, the normal distribution, let me do a little picture up here. The normal distribution had negative z-scores and on the left of the mean, and positive z-scores on the right of the mean. All right. Now, for the chi-square distribution, in this case, it starts at 0 and goes all the way indefinitely to, but never touching the horizontal axis, just like the normal distribution. But as opposed to that, it only includes positive values. It doesn't start from a negative number to a positive number. It starts from 0 to all the way to, well, what really big number. As we mentioned in the previous page, the chi-square curve is right skewed. All right. And again, as the number of degrees of freedom increases or becomes larger, the chi-squares the chi-square curves look increasingly like normal curves. You saw the picture in the previous page, right, in which smaller degrees of freedom is more skewed, larger degrees of freedom looks more like a normal curve. Well, in this case, critical values as opposed to the normal distribution. For normal distribution, what did we use? We used inv t. And for t distribution, we use the inv norm and inv t for the t distribution. However, for critical values using the chi-square distribution, unfortunately, there is no calculator command. So in this case, what we're going to use is a table of values, a table called A4, and the degrees of freedom is n-1, very similar to that of those degrees of freedom from the t distribution. All right. Now, very important note, table A4 as opposed to, well, the chi-square distribution as opposed to the normal distribution and the t distribution, this one comes from the right. We're going to look at area, cumulative area from right to left, as opposed to the normal distribution, in which you might remember how we did this. A, which is the low, and B, which is the larger. All right, so we went from left to right, which is the most common convention. Every time we look at numbers, we go from left to right. In this case, we are going to go from right to left. All right, so let's look at some examples on how to find the chi-square critical values for a couple of situations, and then we're going to apply this to some hypothesis testing. Okay, so let's see what we have. So find the chi-square critical value having an area of 0.025 to its right with 12 degrees of freedom. So that means that in a situation, the sample size for whatever the situation is 13, but we are going to use one less than the sample size, which is 12 degrees of freedom. So I'm going to go to the right again. Let me show you this graph. Notice how this graph is skewed to the right and has only positive values. Notice it doesn't have any negative values, like the mean in the middle, negative values to the left, positive values to the right. So in this case, this one is going to go from 0 all the way to infinity, if it will. So what does that mean? This means that alpha equals 0.05. Now I'm going to show you how to read the table for the chi-square distribution. So this one you will have it in a separate file. So in this case, well, I will explain soon why do I have them highlighted in different colors. So in this case, we're looking for alpha 0.05, which is this one that I have highlighted in yellow, and then the degrees of freedom is 12. So I'm going to go down to the number 12, and the number that coincides with 0.05, which in this case is 0.025 actually, is 23.337, which is this number. So 12 degrees of freedom, 0.025 to the right. So how are we going to do this? Well, just do this. And in this case, chi-squared critical equals 23.337. So because it's on the right, well, we're going to shade to the right. Okay, we're going to shade to the right. So that means when we conduct a hypothesis testing, if our statistical value falls in the unshaded region, that is a number less than 23.337, we fail to reject the null hypothesis. And if our statistic value would fall in the shaded region, that is the statistic value is bigger than 23.337, well, then we reject the null hypothesis because we would have enough statistic evidence to support our claim. All right, let's look at another example. So find a chi-square critical value having an area of 0.05 to its left. Well, here we need to be very, very careful because in this case, for 0.05 to the left, we're going to go to the left of the graph. This is our bound, and I'm going to shade over here. Now, be careful when using the table to interpret this 0.05 to the left. 0.05 to the left (0.05 to the left) means 0.95 to the right. All right. So because if this little chunk is 0.05, the remaining from the right, 0.05 from the left, rather, the remaining from the left would be the complement of 0.05. And what's the complement of 0.05? Yes, 0.95. So I'm gonna go 0.95 with, well, it doesn't say how many degrees of freedom. Well, I'm just gonna make this up. That's 7 degrees of freedom. So with 7 degrees of freedom, I forgot to type it here, your file will actually have the number of degrees of freedom. Well, in this case, 7 degrees of freedom, which is right here, and 0.95, which in this case is 2.167. Okay, so in this case, the chi-square critical, notice it's not an X. It's like curvy over here, and this one is actually diagonal. So this is 2.167. So that's the critical value. Now, possibly one of the trickiest ones is when it comes to find the critical values for a two-tailed test for a variation test. So for a chi-square with 20 degrees of freedom, determine the two critical values that divide the area under the curve into a middle 95. And, well, suppose you didn't read this. Well, 0.95, it's in the middle. We are going to have then a two-tailed, one tail over here, and the other tail over there. All right, if 95 is in the middle, well, this means alpha equals 0.025. I mean 0.05 rather. But this 0.05 splits into two, alpha over 2, the alpha over 2 here, and another alpha over 2 here. Well, how do we interpret those? Well, number one, well, that's alpha over 2 of 0.025, and another alpha over 2 of 0.025. But ultimately, this 0.025, we don't read this 0.025 from the left, actually. So in this case, that's why I got this table and I highlighted each number with colors. So if you notice here, If a test is to be conducted with alpha of 0.1, its complement, the complement of 0.1 is 0.9, because if you add these two numbers, you get 1. If a test is to be conducted with alpha equals 0.05, its complement would be 0.95. Because if you add these two numbers in yellow, you get 1. They're complements to one another. If a test is to be conducted with 0.025 alpha, well, on the other side is 0.975. And so on and so forth. Then the purples with the purples and the pinks with the pinks. Notice how both pairwise add up to 1 because they're both complements of one another. So in this case, we want two outside areas of 0.025. So I'm going to go to 0.025, which in this case is the orange and the orange. So for the two orange columns, I'm going to go, because we want 20 degrees of freedom, I'm going to go all the way to the row with the number 20, and I'm going to go with the first from left to right, which is the one for 0.975, in this case 9.591, and the other orange one for 20 degrees of freedom, which in this case is 34.170. Alright, so in this case, we're going to have two chi-square critical values, one to the left, which is 9.591, and another 34.170. Alright, so two of them. So, and again, these are going to be our bounds, and we're going to do a statistic value, compute a statistic value. Well, in this case, if it falls between 9.591 and less than 34.170, then we fail to reject. But otherwise, if it's less than this number, but larger than that number, then we have enough evidence to support our claim. So now let's do some hypothesis testing, actually. Well, I think at this point you know how to conduct hypothesis test. We need the whole and the half, we need to shade our region, we need to calculate a critical value. Well, in this case, I've just showed you how to find critical values for chi-square distribution and a test statistic. You know, the test statistic for chi-square is simply the sample minus 1 times the standard deviation of the sample squared divided by the standard deviation of the population squared. So those are the only two parameters that we work with: sample size, sample standard deviation, and population standard deviation, which is actually from null hypothesis. You will see how this works. All right, let's look at one example. These are going to be I think they're very short, as opposed to hypothesis testing when we did for the mean and for the proportion. Well, let's see. The manager of a repair shop that service office copy machines is concerned that the standard deviation of the arrival time of a repairman has exceeded 30 minutes. Well, has exceeded. I think this is going to tell us which side of the tail is going to be. Exceed is larger than, so it's going to be a right tail test. A random sample of 24 service calls has a standard deviation of 33.4 minutes. Investigate the manager's concern using a hypothesis test with an alpha of 0.05 significance level. Well, in this case, parameters, and in this case, the number of calls, which is 24. And the standard deviation of the sample, so the sample of 24 service calls had a standard deviation of 33.4. And then the one that is believed will exceed 30 minutes. All right. So let's state the null hypothesis and the alternative hypothesis as usual. the ho and the ha. All right. So, well, in this case, exceed 30 minutes. That means that sigma equals 30 minutes. Well, what is the logical opposite of this sentence? Well, sigma less than or equal to 30. All right. Now, this means, well, look at the direction of the inequality sign. This is going to be a right-tailed test. Well, so let's do that right tail. Let's shade it. And let's shade and find the chi-square critical value for this. All right, so let's see. In this case, alpha equals 0.05 with degrees of freedom, which is 1 less than the sample size, that is 24 minus 1, which equals to 23. So I'm going to go to the table, 0.05, and degrees of freedom all the way to 23. It's going to be a little bit hard to read. Well, 0.05 this column, and 23 is right here. I'm going to go 23, and this is going to be 35.172. This right here, this one right there. So 35.172. Okay, now let's calculate our test statistic. Well, so all we do is write down the formula chi squared equals n minus 1 times the standard deviation of the sample square divided by the standard deviation of the population square. In this case, all we have to do is plug in the numbers. So n minus 1, that's 24 minus 1 times 33.4 quantity squared divided by 30 squared. If we use a calculator, you should get the following, 28.51. Now it's time to compare. It's time to go to the chi-square graph and determine whether this is we have enough evidence to support our claim or not. Well, it turns out that 28.51 is a number that is less than that of the critical value. So for this reason, we fail to reject. Fail to reject because there is not enough evidence to support our claim. All right, so let's have a look at another example. All right, let's look at okay, so a professor tries to design a 100-point test in a way that the scores will have a standard deviation of 10 points. All right, a recent sample of 20 exams has a sample standard deviation of 13.9. Determine whether the professor met his goal at the alpha 0.05 significance level. All right, well, so let's see. This one might be a little bit tricky in the sense that how are we going to how do we know whether this is two-tailed, a one-tailed, and if it's a one-tailed, is it right-tailed or left-tailed? So let's see. In this case, we don't see anything like exceed or is less than, so this is, in this case, it's going to be a two-tailed because the scores will have a standard deviation of 10. That means standard deviation equals to 10. But well, when we have the equal sign, where does that go? That's the ho, all right? The ho indicates equality, and the ha never has the equal sign. Again, why is this sigma not equal to 10? Because in this case, well, it's the test is being designed so the scores have a standard deviation of equal to 10, not less than or equal to 10, not greater than or equal to 10, actually equal to 10. And well, the not equal goes to the high. Sample size is 20 exams. Standard deviation of the sample is 13.9. And standard deviation of the population is the one that is one to be obtained. The one from the null hypothesis. Okay, so let's see. So in this case, this is a two-tailed test. So two tail, one tail here, the other tail there. One tail, another tail. Therefore, we are going to find two different critical values. Okay, two critical values with alpha 0.05. This means split into 2 alpha of 0.025. Okay, so this is how are we going to calculate that or obtain those critical values. So we're going to go to the table. 0.025 to the right, its complement would be 0.975, and we're going to go down to the number of degrees of freedom. In this case, n equals 20. Degrees of freedom is 1 less than the sample size, 19. So I'm going to go all the way to 19. I'm going to go to 19. And then the first critical value from the left is 8.97. That's the orange one. And the other one will be 32.852. Okay, so those are going to be our critical values. .907 and 32.852. Okay, so it's time to calculate our test statistic. So chi-squared is n minus 1 s squared over sigma squared, which is 20 minus 1 s squared, which is 13.9 squared divided by the standard deviation of 10 squared. All right. Putting all this in the calculator, 20 minus 1 is 19, and then whatever that is squared divided by 10 squared, which is 100, we get 36.719. So 36.719 is a number that is larger indeed than 32.852. And for this reason, we have enough evidence that the alternative hypothesis wins. So we reject the null hypothesis because there is enough evidence to support our claim. All right, so let's do one more example. Well, in this case, we have a sample of 10 scenical capsules that have weights in milligrams in the table below. All right, so in this case, we're given data to put in our calculator and do the stats ourselves. All right, so at the 5% significance level, that means alpha equals 0.05. Do the data provide sufficient evidence to conclude that the standard deviation of the weight of all scenical capsules is less than 2.0 milligrams? So let's state the null hypothesis and the alternative hypothesis. Ho and the ha. So, the standard deviation less than 2.0 is less than, and standard deviation greater than or equal to 2.0 for the null hypothesis. Keep in mind again that this never has the it never has the equal sign for the alternative. All right. So in this case, well, what are we going to do? So we are going to store in L1 in our calculator, then do one var stats to get the standard deviation of both the sample and the, well, actually the sample only, the one from the population is given, it's 2.0. Right? Be careful with this part. The only piece of information that is obtained from here is little s, in this case sx in the calculator. And once you input all these numbers in your calculator, if you want to stop the video and do it on your own, you should get 1.055. All right, and well, so far the claim is kind of met. Well, 1.055 is a number that is less than 2.0, but now we need to get statistical evidence to show that we have strong evidence. Well, n equals, in this case, the number of capsules that were weighted, in this case 10. Alright, so in this case we're going to do a right-tailed alpha, of 0.025. I mean 0.05, not 0.025. Oops, it's right here. So we're going to look for the chi-square critical, and I'm going to shade the left part of the graph. Okay. Well, this little chunk from the origin from 0 to 0.05 means that this is, and again, this is like the tricky part, because we read areas from right to left. So if this is 0, this is 1, this huge chunk would be the complement of this little alpha. The complement of 0.5 is 0.95. So 0.95 with how many degrees of freedom? So degrees of freedom, n equals to 10. Degrees of freedom will be n minus 1, which is 10 minus 1, which is 9. So I'm going to go to the row with degrees of freedom equals to 9 and the column of 0.95, which in this case is 3.325. All right. Okay. So it's time to get the test statistic for this, and for this all we do is chi-squared equals n minus 1 s squared divided by sigma squared. In this case 10 minus 1 and s, which is 1.055 squared divided by 2.0 quantity squared. If you put this in the calculator, you should get 2.504. And alright, let's see what we got. The number 2.504 is a number less than 3.325, which actually falls in the shaded region. For this reason, we reject. We have strong evidence to reject the null hypothesis, because there is enough evidence to support our claim. Alright, and this is going to be the end of this video. On the next video, we're going to look at the application for chi-square distribution for the goodness of fit test. I'll see you in the next video.